Now, let's consider the power which is delivered to the load. In many situations, we have a certain amount of power which is available here in a generator, here in the left of the transmission line. We have a transmission line, and we have an end which can be a device which needs this power, or can be just an antenna. For example, if we have a transmission, a wireless transmitter, this can be our device which is actually providing a signal, and we have a remote antenna with a certain, I don't know, a coaxial transmission line of some meters of length. And what we want is, we want to maximize the power, we want the best efficiency possible, we want to maximize the power which transfers from the generator, from the transmitter, to our antenna at the end of the transmission line. So what are the conditions that have to be satisfied in order to make this power transfer a maximum parameter? What is the best efficiency in this case we can achieve? Okay, we can just write the equations of power. Power here is related to the product, a real part of the product of voltage and intensity here at the input port of the transmission line. Okay, we can express here this voltage and current here relating the impedance at this point, at the input of the transmission line. This impedance and is related to the real and imaginary part of the impedance. We can split the impedance into their components. Also, the generator maybe is not Z0, maybe it also has some complex impedance at the output. This happens sometimes. So, okay, let's express also the impedance of the generator in the real and imaginary part. We substitute here in the equation, and we obtain the power transfer to here, actually, to the input of our line. Okay, we get this expression. The interesting case here is we want to maximize this transfer power. How to maximize this? Okay, let's find the maximum of this expression. Let's take a derivative and make it equal to 0 with respect to the real and imaginary part of the input impedance in this case. Okay, if we maximize the transfer power, we get these equations have to be satisfied, and at the end this means the real part of the generator, if we want to transfer the maximum amount of power, has to be equal to the real part of the input of the transmission line. And then what happens with the imaginary part? Well, they don't have to be equal, they have to be just opposite. And actually, if we express this in complex numbers, the input impedance of the transmission line have to be conjugated, the conjugated value, with respect to the impedance of the generator here. This is what is called the conjugate matching situation, which maximizes the power which is transferred to the load, and actually in this case this maximum corresponds to this expression, which involves the voltage of the generator and the real part of the impedance of the generator. Now, the typical situation we are going to face is the fact that the impedance of the generator in general will not be exactly the same as the load impedance. This happens, for example, with antennas very usually. For example, in wireless communications, the antenna is not having exactly the same impedance as the generator. If you don't make nothing about it, then part of the power of the generator is going to just reflected towards the generator. That is going to cause problems to the generator, and we are losing efficiency. So we are not transmitting all the power we have available. So we are losing, for example, coverage in a wireless communication system. So we have to do something about it. And something we have to, it is routinely done, is we can use a matching network which actually interconnects the generator and the antenna. So let's assume the generator has a piece of transmission line at the output, the antenna has a different impedance. So if we use a matching network which is somehow able to transform this impedance of the antenna into a matched impedance to respect to the generator, then we will achieve maximum power transfer. So how are we going to design this interesting matching network? Well, there are different technologies that we can actually use for this purpose. If we use, for example, low frequencies, say below 100 megahertz, in short waves, for example, it is quite routinely use concentrated parameters. So we can use coils or inductors and capacitors. A network involving this. A few of these elements are able, with proper parameters and proper configuration, connection, L or pi configurations, we can actually match this impedance to the generator impedance. However, when we climb above, say, 300 or 400 megahertz or several gigahertz, for example, in wireless and Wi-Fi, for example, applications, then the inductors and capacitors, they don't work very well. So it is much better to use transmission lines to do this matching. And that's what we are going, because we are now in the transmission line chapter or lectures. Let's learn how to use transmission lines to provide a matching network. What we are going to see here is the stub matching technique. It is very standard in radio frequency applications. The situation here is the following. We have, as before, a load impedance here, which is different from the characteristic impedance of the line, or a generator here in the left. And now we want to provide a matching network, which is actually composed only by transmission lines. And in this case, transmission lines of the same characteristic impedance as the transmission line of the generator. It can be done like this, as simple like this. So in this case, what we are going to do is the following. We are going to provide an open-ended line, transmission line, which is connected in parallel to the main line, which is relating the generator and the load. So you see here we take a piece of transmission line, we left it open at the end. It can be shorted as well, but the example here is using an open circuit case. This piece of transmission line with an appropriate length L2 is connected in parallel to the main transmission line. And the point of connection is critical, because this separation distance here, L1, from the load and the point of connection has to be accurately calculated in order to provide the matching situation, or the desired matching impedance condition. You see here an example of application of this stub matching, in this case with microstrip lines. What you have here is just a single transistor RF amplifier, or microwave amplifier, in this case a 10 gigahertz frequency. You have here the input and output ports. These ports actually are connected to a transmission line here, which is just a microstrip circuit. You see here, this is the microstrip at 50 ohm transmission line. And you see here the input port of this transistor has an impedance which is not Z0. It is different to the transmission line. So if we do nothing about it, we will have a reflection here on the input port. Also, the output port is the same. The output impedance is not Z0, so we will have a reflection here at the end. So we have to correct for this. The way to do is to do the correction, or the matching, is we include a stub. This is this piece of transmission line. Is left open at the end and is connected here in parallel to the main line, which is connecting the input port with the input port of the transistor. So this is actually the situation we are just describing here. We have one matching network at the input of the transistor, and we have exactly another case of another example, the same technology at the output of the transistor, because the output of the transistor is also not matched to the impedance Z0 of this transmission line. So we do the same two times, two calculations, two different values at the input and at the output. So we have 2 degrees of freedom. We have to calculate what is the length of the stub, and we have to connect it precisely at the right distance from the load, these L1 parameters. So let's see how can we determine these two distances using the Smith chart. It can be done algebraically, but we have introduced the Smith chart before, so let's use it for this particular example. Well, the first thing that we are going to study briefly is, okay, what is the impedance and admittance at the input of the stub. So we are using a piece of line which is left open circuit at the end. So the question here is, okay, what is the impedance and what is the admittance at the input of the line? So here we have an example, we have a piece of line, 0.1 lambda, and we want to determine what is the impedance. Okay, we start here at this point. This is the open circuit, we know this. Now, we are going to actually move here towards the generator 0.1 lambda. Okay, that's easy. Let's take the Smith chart. We move 0.1 lambda towards the generator, and that's it. That's the solution. That's the impedance, and the input is purely imaginary because a real part would imply some loss of power, some dissipation. There's no dissipation in this case. We are assuming a lossless transmission line in this example, so it is pure imaginary number. What happens here is this impedance parameter will have to be converted to admittance in order to be used in our example. Why admittance? Because when you connect two loads in parallel, the admittance of the resulting connection is just an addition. If you make the parallel connection with impedance, the calculation is not so straightforward, so it is practical to work in admittance when you have to connect something in parallel. So, okay, we can start from the open circuit here. We have a zero admittance at this point in a Smith chart when it's used as an admittance chart, and then we do the same. We rotate 0.1 lambda towards the generator, the same sense as before, and we get the admittance at the input. And you see here they are both opposite, you know, because impedance and admittance are just opposite complex numbers, so of course they are occupying the opposite positions in the Smith chart. Okay, that's the solution. So we know what is this parallel line here, connected line here, doing when we connect at certain point of the main transmission line. Now, let's find the solution of the whole problem now. We have the impedance, the load impedance here at this point. We know this parameter, so we have to measure our antenna or our device here, so we know the impedance. So one is normalized, it's just a point in the Smith chart. If this point is here at the center, we don't need to do anything because the reflection will be zero in this case. But if we are away from the center, we have a reflection, so it is interesting to introduce a matching network, in this case made with transmission lines and stubs. Okay, that's the point, we start. Now, this is this point. We move here towards the generator, towards the connection point of the stub. What's going to happen here? Well, we can, as before, we can, instead of using impedance, we can modify this impedance or change into admittance and work with admittance directly because it is more convenient for parallel connections. And now we start from, this is the admittance of the load, and then if we move towards the generator some, at this moment, unknown length, L1, we move along this line, okay? So moving towards the generator is, we preserve the radius, so the amplitude modulus of the reflection coefficient does not change at this point because we are moving along lossless or low loss transmission line. Then only the phase changes towards the generator. We are moving along this arc. Where do we need to stop? Because actually this change of phase is related to L1, which is the length of this transmission line here. So what should be this length here? Well, that's important, because if we stop at the correct number, we will succeed in matching the impedance. If not, we will actually have an incorrect matching. So we have to stop at a point where the real part of the admittance is equal to 1. And this circle here, which is bold here in black, this circle is the real admittance equal to 1. We have to stop at this circle. For example, at this point, that would be also another possible solution, stopping at this point here with a slightly longer transmission line, L1 parameter. But let's stop here because this is a short line, so L1 is a very small piece of line. Why do we want to stop at this point? Well, the reasoning is the following. What is this stub in parallel going to provide us? Well, the stub in parallel, because this is a lossless line, is adding only an imaginary number. It's only adding an imaginary part of admittance. So whatever it has to be done with the real part of the admittance has to be provided by L1, by this first piece of the transmission line. So we have to stop at the correct real part of admittance, because the stub that we are going to connect in parallel is going to do nothing about the real part. So the real part has to be determined here at the very first step, determining L1. Okay, we start here. We are in the real part of our admittance value at this point, at this particular point input of the L1 section of line. Now, what is the situation? From the reflection point of view, the reflection coefficient point of view, we are at the same situation as before. We have done nothing because the reflection coefficient here and here are the same. Only the phase has changed. But we have still a reflection condition here. Why do we have a reflection condition? The real part is correct? Yes, the real part is correct. We have admittance equal to 1. That's perfect. What is the problem? The imaginary part. We have an imaginary part here, which is this value here. It belongs to this circle, which is non-zero. So we have to cancel this imaginary part. And how are we going to cancel this imaginary part? Well, if we connect in parallel an imaginary or a load which has an admittance which is imaginary and happens to be just opposite in value as the value we have here at the input of the first transmission line section, we will cancel the imaginary part and then we will be in the ideal matching condition. So that's what we have to do. So we are going to use now the stub. This transmission line, which is open circuit at the end. Now we have to make this transmission line the correct length of the transmission line in order to provide an input impedance that just cancels this imaginary part that we have here in the previous situation. How are we going to do that? Well, we know the value. This is the imaginary value the stub has to offer at the input. Okay, let's determine the length. We just make the L2 length of the stub line the correct length in such a way we get the imaginary part which we desire. Now, the imaginary part offered by this stub here at the input is just cancelling the imaginary part of this input of the first segment of the transmission line. And now if we actually make this connection, these two imaginary parts cancel each other, and we obtain just the center solution, which is admittance equal to 1. What this means is we have a matching, a perfect impedance matching or admittance matching condition, and our matching network is complete.